Hi, this is Alex from devstories.eu. AstroPython, Python for Astronomy, episode 11 of 15. Every pixel on a telescope detector is a flat, discrete square, but the sky is a continuous, mathematically complex curved sphere. Mapping a point on that flat detector back to its true position in the universe is a messy geometric problem. World Coordinate Systems, or WCS, is the mechanism that decodes that geometry. WCS acts as the ultimate bridge between hardware and physics. It provides the mathematical transformation required to turn a pixel coordinate into a world coordinate, like right ascension and declination. In astronomical data, these transformation rules are usually stored as standardized metadata inside a FITS file header. The header contains specific keywords defining the reference pixel, the physical coordinates of that pixel, and the rotation or scaling matrix used by the telescope. Astropy reads these keywords and builds an active transformation object that models the entire focal plane. Before doing any math, we must clear up a constant source of indexing confusion. The FIT standard defines pixel coordinates as 1 indexed, meaning the very first pixel on the detector is pixel 1. Python, and therefore NumPy, is 0 indexed. Astropy resolves this duality through two different layers. The older low-level API is not a unified indexing system. It requires you to explicitly pass an origin argument of 0 or 1 every single time you transform a coordinate. But the modern high-level shared Python interface operates entirely on Python's zero-indexed convention. It expects zero-based pixels from you and automatically handles the offset to the FIT standard internally. Here is the key insight. The high-level WCS API makes coordinate conversion incredibly concise. Say you have located a bright star in your image array at pixel x equals 30 and y equals 40, and you need to find its true position in space. First, you read your FITS file header using Astropy's input-output tools. Next, you initialize a WCS object by passing that header directly into the WCS class. Finally, you call a method named pixel-to-world on that WCS object, passing in your x and y pixel values of 30 and 40. The method evaluates the projection math and returns a standard Astropy sky coordinate object. This object contains the physical coordinates and is completely aware of its reference frame, such as ICRS. The beauty of this shared interface is that it shields you from raw numbers. Instead of returning a generic array of floats representing abstract degrees, it gives you rich objects that understand their own physical units and coordinate systems. You can take that sky coordinate and immediately use it to cross-reference a star catalog. The system works exactly the same in reverse. If you have the coordinates of a known galaxy and want to determine exactly which pixels it occupies on your camera sensor, you call the method world-to-pixel on your WCS object. You pass in your sky coordinate, and it returns the exact x and y floating point pixel positions. The high-level WCS API isolates your application logic from the underlying projection math, meaning your pixel-to-sky conversion code remains identical whether you're working with a flat radio map or a deeply distorted wide-field optical mosaic. That is all for this one. Thanks for listening, and keep building.